I'm Tom Charton from National Grid Electricity Transmission in the UK. I'm by background more an asset manager, but yeah, we collaborated in this project with GE to look into what Seapath can provide for us, and our focus was mainly to look at the real-time performance and deterministic performance of Seapath for protection applications. So whilst there's a lot of commonality with RTE's approach, our focus here was more to look into protection. And quick overview of what we're going to touch on, a bit of the environment that we operate in, the kit that we look after in terms of primary and secondary equipment, why we're looking for virtualization and why did we look to Seapath, what kind of hardware worked best for us in our pilot, what software architecture did we end up with, and how did we tune the system for real-time performance, how do we scale it up for a substation at transmission level. Then we already seen some things about redundancy and clustering. How do we engineer it? What have we learned, and what we're going to do in future. So just a little bit about National Grid. We're the transmission owner. That is slightly different to probably most of you. We just own the network. We don't operate the network. There's a separate national system operator, and we look after the transmission network in England and Wales. There are 2 more TOs in Scotland and then Northern Ireland as well. As National Grid Group, we also run transmission and distribution in the US as well, and we've got various other businesses doing investing in renewable energy and the likes. Our network is mainly 400 kilovolt transmission with a few 275 kV lines, and it mainly follows our motorway network. What we're all about is what you see at the bottom right. That's what we're all about, availability. So that's our main concern. All the designs and the processes we put in place is to maximize the availability of our network to our customers and consumers. To deliver that, the primary assets is what the high voltage equipment includes. Looks like this. This is a good example of a double bus bar substation with feeders coming in from the top, and at the bottom you'll see transformers and reactive plants. So that's what we're protecting. To protect and control all these assets, we've got around 5,000 bays, so we're grouping functional groups by bays. And overall, we've got around 15,000 bay devices to look after. It's not huge, but yeah, it's significant. And the kind of functions that we deliver with the secondary equipment is obviously most importantly protecting the network, then control, automation, settlement metering for the financial settlement, system monitoring like PMU data is now increasingly important for voltage stability assessment. We've got our own comms network, our own fiber network, and cybersecurity also increasingly important, and asset health monitoring, and yeah, quite often underestimated, but everything depends on our DC supplies in our substations. Our legacy architecture for protection, automation, and control looked a bit like this. Multiple devices delivering small function groups each. So we're interfacing the control center through redundant gateways. Then we might have a separate machine for the HMI or the substation control point. We might have a monitoring server, then automation servers for automatic reactive switching and automatic tap change controllers. And then in each bay, and typically our substation would be anything from 10 bays to about 50 bays, we would have groups of IEDs that implement the protection and automation control functions. We're increasingly now looking to process bus for the primary plant interface, but most of our installed base is still hardwired to the primary equipment. So what have we moved to? Our current design, the first stage is the virtualization of all the control and automation. So the current approach is use redundant servers with a hypervisor on top, and then 4 VMs with HMI and gateway functions on VM1, tooling VM2, then security, domain controllers VM3, and then VM4 will be a monitoring VM, and that will be fully duplicated and interact with the National Control Center. So we already cut back a little bit on the diversity, but we're still retaining all the bay equipment, typically up to 5 IEDs per bay, so that can add up quickly. So why are we driving now to virtualize even further? If we look at a substation, we might find in any substation about 100 different types of devices to manage. And they might range from legacy equipment like electromechanical up to modern digital relays. They stay in service for around 20 years, or the electromechanical even longer. We do biannual tests, and they provide self-supervision, which is great, but it's still a lot of assets to manage. And also when we look towards the cost, it's very expensive to look after all these devices. We expect virtualization will deliver a massive saving for us in terms of OPEX. Another key driver, why do we need to change what we do? We can't deliver what we need to deliver for net zero just by carrying on as we do now. If you look at our 2050 net zero commitments at the top right, the growth figures are eye-watering, and the current supply chain and our in-house capability can't grow at that rate. So we need to do something a little bit different. And hence why we looked for further virtualization. So in this model, we're adding further VMs to the architecture to manage the protection, the real-time protection, and we're looking to Seapath to deliver that hypervisor capability for the real-time performance applications. We're trying to address obsolescence issues to move to that infrastructure as code kind of approach, address cybersecurity concerns, and break that hardware-software dependency. Our automation functions like automatic reactive switching or tap change controllers, the logic remains the same, and if we just keep the software, we can just swap out the hardware that delivers the function without retesting the software every time. System access is a key constraint, so by reducing the number of times we actually need to attend a substation, we gain a lot, and we can also scale up delivery times by optimizing the engineering process, being more digital, automated, and templated. So. Why Seapath? Probably don't need to sell it to you, really. You're probably all already converted. But yeah, we're looking for diversity in the marketplace. We don't want all eggs in one basket. We're looking to have different options for us. And leverage the open source benefits of fast innovation and the long-term technical support, which is why Seapath, with its OT focus, seemed the right choice for us. This looks familiar from the earlier presentation. So we went with the standard Seapath build. We've got a hardware cluster, 3 machines, a KVM Yocto on top of that with a QEMU for hardware emulation. All these components look very familiar and are identical to what you've seen earlier. We used, because the bottleneck is always the sampled value processing, we look to bypass the vSwitch and use a PCI pass-through to send the sampled values directly to the VM that processes the sampled values. And initially, we used a pacemaker for cluster management, but we also looked into some alternatives to pacemaker. And yeah, the build process is managed with Ansible, goes without saying. What have we learned with regards to the hardware? So we wanted to develop something that's hardware agnostic. It should run on x86 or ARM process. For now, we have just validated the classic x86 kind of architecture, but we might look into an ARM processor-based machines as well. IOMMU must be supported, and the system processor frequencies is really important. Don't rely on the boost mode, because most of our processing is fairly constant. The SV processing is there all the time, and yeah, temporary boost mode doesn't really help us. Another key thing is temperature range, cooling and life cycle. We love totally passive devices, so no active cooling or any moving parts. Why? Because we've got around well over 300 substations to maintain, and we haven't got the capability to go around and swap out fans and clean filters and the like. So we need the kit to fit and stay in for 10 years and then be replaced. We tested 2 machines, one at Vantech ECU 579 and a Velatech machine as well. So regarding the software architecture, we landed on a model with Seapath, and then on top of that VMs, and then Docker inside the VMs. And we looked at Docker Swarm as well to ensure containers can communicate across the nodes, but it's important to check the implications for jitter. Yeah, optionally, PDK can be used to accelerate the packet processing. Yeah, as I mentioned earlier, we use PCI pass-through. SRIOV can also be implemented if you need to pass the samples to another VM, to multiple VMs. But because we only passed the samples to one VM, we didn't implement it in our trial. Okay, yeah, so the main challenge was sampled value processing, and we implemented Yocto, and we pinned the hardware resources to the VM and implemented IRQ offloading, and we used IoT brokers to communicate between the Dockers in that VM. And the best one seemed to be 0MQ. For SV and Goose in our experience. So this is my favorite slide. It tells me exactly how I build my virtualized platform. I know if I've got 60 bays, I need 3 sampled value subscriber Dockers, because each one of them managed to do 20 streams. But it's worth checking, because this depends on the processor that you're using. So we found one processor managed 20, the other one managed 8. So it's worth validating. So if you have a processor that can do 20 streams, you stick in 3 Dockers for those. You got 60 streams you can process, and then protection Docker. We found there is the performance pretty good. We managed to do around 5,000 overcurrent algorithms, so I think that should be more than enough to implement all the substation functions. And the cores were pinned to those Dockers. And this illustrates really well how it scales up and how you can stack up further VMs for HMI, automation, control, monitoring, etc. On your hardware. So we carried out some tests, lab-based tests. So we had the Linux Yocto test VM that implements the sampled value processing and the protection functions. And we also configured various other Linux. We had one Ubuntu machine and a Windows machine for the management of the pilot. Overall, then we scaled it up to a cluster of 3, more or less identical implementations, and then run some trials. For protection, we used an Omicron to generate the analog signals, did some pre-fault at 1 amp, then we injected a fault like 5 amps with the threshold being at 1.5 amps. The merging units then would do the A to D conversion and publish the sampled values onto the process bus via the Ethernet switch that would go through a Seapath to the sampled value processor, and that would then communicate with the protection Docker application that would detect the overcurrent condition and issue a trip goose back down the stack through the Ethernet switch to the merging unit. The merging unit publishes the trip signal, and Omicron records the round trip time. So that was the approach we'd taken to validate. And yeah, the results we got, we run quite a lot of repetitions, just over 44,000, and average time was around 5.5 milliseconds for the round trip. And yeah, very good determinism around the operating time. So none of them went beyond 6 and 6.6 milliseconds, and standard deviation is pretty low. The 6 milliseconds round trip time roughly splits up into 2 milliseconds on the merging unit, 2 milliseconds in the Seapath platform, and 2 milliseconds back when the merging unit receives the trip signal. So going forward, what do we need to do to make sure virtualization is reflected properly in the IEC standards? Firstly, I think the virtual IAD definition in -1, -2, and -3. Secondly, we probably need to look at the engineering process. And then thirdly, some new logical nodes need to be introduced. I think all that good work's ongoing, so it's good to see, and we obviously support this. I won't go into all the details because of the time. What have we learned? So we're pretty confident that the current hardware could support a protection system that would fit our substations, that would scale up to 50 bays. Is that what we need? We're still really keen on fanless options. So yeah, server OEMs love to talk to you about what we can do to push the capability with fanless options. Deterministic behavior could be delivered just on a general application server and the Seapath hypervisor, which was what we wanted to validate. But yeah, our model is to look for a productized version of Seapath. We probably less capable getting involved ourselves. We look to buy in Seapath as a licensed product. Yeah, we validated the Seapath architecture as a whole, real-time performance, and performing on an Intel architecture. So yeah, overall, we're very happy with the outcomes. What we're going to do next is yeah, have another look at future hardware platforms and around clustering, how we're going to cluster. We looked at a technology with floating IP to make sure that all the control applications act as one virtual device, even if they're clustered on multiple hardwares, but the protection applications still act as multiple devices to give us that resilience for the protection applications. Interoperability is key for us. Deploy different protection virtual IDs within the VMs on the machine. Improve the engineering process with more templating through basic application profiles, which is something that's ongoing at the moment. And yeah, we're committed to putting a pilot scheme on the network before 2030. So that's it in a nutshell. Thank you for your patience. If there are any questions, not sure I can answer them, but if need be, I can ask. Yeah, got one question.
Hi, Marco Galvagno from Tesmec. You were talking about PCI Express pass-through. Which was the need of using this pass-through for presenting the network card to the VMs or for other purposes?
I think it's because the Open vSwitch performance wasn't quite up to scratch for the real-time performance. Do you want to add anything to that, David?
The PCI pass-through is an acceleration, so it speeds up the sample values going to the virtual machine.
From the network interface?
Yes, directly from the network interface to the virtual machine, bypassing the kernel, bypassing any switch. Yeah.
Well, I think in the interest of time, any other questions, come and see myself or our colleagues from GE who've done all the legworks and are probably better qualified to if it's really technical. So yeah, thank you again, and I'll pass on to our next speaker.
Yes, thanks a lot.